So for this lesson, really focusing on the idea of differentiability, which refers to where a function can be differentiated and where it cannot be. If a function is differentiable at some point, that means you can find the derivative there. If a function is not differentiable at some point, that means you cannot find the derivative there. And I'll talk about reasons why you cannot find a derivative. But in general, as it says here, there's 4 ways a function might not be differentiable at some point A. And one is if there's a discontinuity, any type of discontinuity. And we've looked at 3 of them in the previous unit. Infinite discontinuities, removable discontinuities, and jump discontinuity. So if there's a discontinuity somewhere, that means at that point, the function may still be defined, but you can't differentiate it there if there's a discontinuity. Another one is if there's a corner. And a corner, one way of understanding what a corner is looking at the limits of the derivative. So as you see here for a corner is if essentially if the derivative from the left and the right aren't the same. The derivative exists from the left and the right, but the derivative from the left and the right is not the same. A cusp is when the derivative from the left and the right approaches infinity, positive or negative infinity, but they're still not the same. And then if there's a vertical tangent, which is if the derivative as you approach from the left to the right equals either plus or minus infinity, but they are the same. That's it. As expected, this should make a lot more sense with a visual. And here's a visual. And so, for example, this is one of each of the examples from above. So right here, I can see there seems to be a vertical asymptote at -1. Even if it's actually not a vertical asymptote, it's meant to be. So actually, I'll just draw that a bit more neatly. There's still clearly a discontinuity here. So right here, we have a discontinuity. So so f of x, this particular function is not differentiable at -1. Right, the function is defined at -1. Notice at -1 there's a closed point at the coordinates -1, -2, but the function is not differentiable there. You can't find a slope of a tangent line at that point. Okay, so a corner is what we see right here. That's a corner. Notice from the left, the derivative is looks like a line segment, and it looks like the derivative is roughly 2/3. From the right, it's some sort of curve, but it's a different slope. So I can find, there's a slope from the left, there's a slope from the right, but they're not matching the same value. And every time we see that, there's a corner. All right, next, a cusp is what we see right here. Notice if I zoom in as much as I can, this point, if I look from the left, this line is getting steeper and steeper and steeper, but going down, which means the slope is from the left, the slope of this function, or the derivative of this function from the left is approaching -infinity, because it's getting closer to being a vertical line, and a vertical line is undefined. As I approach from the right, it's same idea, except it's going up. If you look at this function, it's going up now, so it's approaching a vertical line, but a positive. So the derivative from the left is approaching -infinity. The derivative from the right is approaching positive infinity. And if I were to be able to keep zooming in on this, if I had it in Desmos, I would just keep seeing a point getting sharper and sharper and sharper forever. And that's a cusp. Notice it's quite different from a corner, which a corner from the left and the right, it's not approaching this really, really sharp, almost vertical tangent. And so lastly, an actual vertical tangent is what I see right here at 0. I can draw, in fact, of all these 3 points, this is the only point I can actually draw a tangent line. And so I will. The tangent line at this point is perfectly vertical. It's kind of hard to see there. Maybe I'll highlight it. Right, I can draw a tangent line right there. That said, the slope of a vertical line is undefined, which means the derivative at this point is undefined. So they're all different, all 4 of these examples. Most of them, it's not even possible to draw a tangent line. At a vertical tangent it is, but it's still, the function is not differentiable there. However, notice as well, this particular function is defined at all these points. It's defined at the discontinuity, it's defined at the vertical tangent, it's defined at the corner, it's defined at the cusp. And if I draw a little arrows on here to show this goes on forever, this function has a domain of all real numbers, but it's not differentiable at all real numbers. All right, so now let's look at 3 different examples. And for each of these, I encourage you to graph with technology to kind of visualize it. And what I'd actually highly encourage you to do is to pause this video and look at functions a, b, and c, graph them with technology, and think about what kind of discontinuity are you seeing. And I'll show these in a second. And so, for a of x, let me look at the graph. So here's a of x. So this is what the graph of a of x looks like. And this is a cusp. And notice if I zoom in on it, I can actually zoom in this as much as I want. Notice it just keeps getting steeper and steeper forever. If I zoom in enough, it looks like it's perfectly vertical. That's a cusp. And so we say there's a cusp when x equals -2. Sorry, x equals +2. All right, that's it. So let's look at the cube root of x. There we go. So what we see here is a vertical tangent at 0. And again, if I zoom in, it becomes pretty clear the tangent line is vertical at that one instant. And again, the slope of a vertical line is undefined, so the derivative is undefined there, hence it's not differentiable. So for this one here, we have a vertical tangent And lastly, for function c of x, the absolute value of sine x over absolute value of sine x over x. I have this. Let me zoom out a bit. And there's actually several places that this is not differentiable. The most obvious probably is right at 0. When x is 0, we have a jump discontinuity. However, we also have all these points here. For example, at pi, and at 2 pi, and at 3 pi, and any multiple of pi, I have these sort of, it looks like it bounces. So it's not differentiable there. I can't draw a tangent line at pi, at 2 pi, at negative pi. I can't draw a tangent line there. So I know it's not differentiable, but what's the reason? And if I zoom in, this is a corner, not a cusp. Again, a cusp is very specific. The 2 points approach this infinitely sharp point. That's not what's happening here. This looks like 2 line segments at this point. So I have corners at any multiple of pi except 0. I have a jump discontinuity at 0. So there's a few things I got to state here. So that's a weird looking 0. So a jump discontinuity at 0, and I have corners at any multiple of pi except 0. So n belonging to any integer and n not equaling 0. All right. So again, the point of this is to get a feeling about what these different kind of reasons that a function is not differentiable is and what they kind of look like. Definitely, if you can visualize the function on your own, that makes it a lot more straightforward. But again, right now, the idea is you would graph these. All right, so the last question is a little bit different. I have a function here, and I'm being uncreative, and I'm calling it f of x. So this is f of x, and it's meant to go on and on indefinitely. What I want us to figure out is where the derivative of this function is not differentiable. So I'm not asking it's not like before, I'm asking where is f of x not differentiable. I'm asking where is f prime of x not differentiable, and why. I'm going to say why, like corner, cusp, whatever. So first thing I got to do is I got to visualize the derivative of this function. Well, that's what we looked at sort of last day. So get a nice marker here. And there's no general one way of doing this, but I would first focus on this line segment that goes everywhere where x is less than 0. That line segment has a slope of -1, and so I can visualize the derivative here as just a horizontal line at -1 going on forever right here. At 0, there is a corner, but again, I'm going to eventually think about the discontinuities of the derivative. But there is a corner at 0, so I can see the function is not differentiable at 0. From the left, the slope is -1. From the right, the slope, I'm kind of estimating here, if I kind of visualize the tangent line here. I don't know, what's that slope? Looks like that. Let's say that slope is about -3/2, -1.5-ish, something like that. Again, I don't actually need to know exactly where it is. I just need to know it's not -1. So let's say, I don't know, somewhere right here. However, as I go this way towards this cusp, the slope keeps getting steeper and steeper and steeper, but is always negative. And the closer I get to that cusp, the closer the tangent line gets to being a vertical line, but still going down, which means I now know the derivative as I approach 2 must start going down forever, but I also know there must be an asymptote at 2. And so I'm going to draw that asymptote right now. And again, this is the asymptote for the derivative. F of x doesn't have any asymptotes. But I can see as I approach 2 from the left, the slope keeps getting steeper but negative, and so I must know it must look like something like this. And as I approach from the right, it's going the other way around. It's, you know, if I could zoom in on this, like if I actually had this graphed in Desmos, you would see that it's a cusp in that it's getting closer and closer to being a vertical tangent right as you get to that point. But from one side it's going down, one side it's going up. Okay, after that, if I look at this last little segment right here, the slope, it's always increasing. The function's increasing, but the slope is going down. It's at its steepest, the closest to the cusp, and as I look at the tangent line, it's getting less and less steep, but it's always going up. So at this point, that means it's always staying positive, but the derivative is, I don't know, doing something like this. It's going down. The key is it's going down, and it's not stopping. All right, so there's a lot of details I don't know about my graph of the derivative, but I know enough to answer the question. So we see in red is my graph of f prime of x, my sketch. Okay, that's it. Now I can answer the question. Determine where f prime of x is not differentiable. All right, so I can see right here it's not differentiable, and that's because there's a jump. And I can also see it's not differentiable at 2 because there's a vertical asymptote or an infinite discontinuity. Other than that, this function is differentiable. I can differentiate f prime of x anywhere else. There's no other corners or other breaks in the graph. And so I can now answer this. I can say f prime of x is not differentiable. At x equals 0. And again, because there's a jump discontinuity. And at 2, because there's an infinite discontinuity. But everywhere else, I know f prime of x must be differentiable. All right, so that's it. Tricky things here, as to be expected.